Have you ever really stopped to wonder what makes things fast? I mean, what really governs how fast something can move? It's not as simple as just pushing harder or falling from higher up. Nope. There's this hidden battle of forces happening all around us, a fundamental physics that shapes our entire world of speed. So let's dive in and figure it out.
Okay, think about this for a second. When something falls, gravity is pulling on it, and that pull is constant. So shouldn't it just keep getting faster and faster and faster forever? But it doesn't, right? Even a skydiver hits a top speed. There's like a cosmic speed limit. Why? What's going on there? Well, the secret is that a fall is not a one-way street. As gravity is pulling an object down, there's this other force that's pushing right back up. It's this constant, epic tug of war. And if you can understand this battle, you can understand the secrets of speed itself. To really get a grip on this, we've got to start at the very beginning of the fall. You know, that one single moment right before the leap, when everything is perfectly still. This is where the whole story begins, with the first type of energy. It's called gravitational potential energy, and you can just think of it as the energy of what if. It's pure stored-up power that's just waiting to be unleashed. The higher up an object is, the more potential it has to fall, and so the more potential energy it's packing. Picture it this way. Our skydiver standing at the door of that plane is like a massive, fully charged battery. All that energy is just stored up thanks to their position way up above the Earth. And the very second they jump, that battery starts to drain, releasing all that power. So as that potential energy starts turning into the energy of pure motion, our skydiver immediately smacks into the second character in our story. It's this invisible force that pushes back on everything. We're talking about air resistance, or as physicists call it, drag. So what exactly is this invisible wall? Well, it's not just one thing. It's kind of like a recipe with a few key ingredients. And this equation you see here, this is that recipe. Let's break down what's in it. Okay, first ingredient, the drag coefficient, or C. This is basically just a number that tells you how aerodynamic an object's shape is. A super sleek Toyota Camry has a low C value. It just slips right through the air. But a big, boxy Hummer? Not so much. It's got to fight the air way, way harder. Next up is A, which is for area. This is all about how much of your surface you're showing to the wind. And what's cool is a skydiver can change this in midair. If they go into a head-first dive, their area is tiny, so the drag is low. But if they spread out like a starfish, they present a huge area, which creates way more drag and slams on the brakes. And finally, we get to velocity, V. And listen up, because this one is the game changer. Its effect isn't just one-to-one, it's squared. That means if you double your speed, you don't just get double the drag. You get 4 times the drag. This explosive relationship is the real reason there's a speed limit for falling objects. All right, so we've got gravity yanking down and this powerful drag force shoving up. What happens when these two forces finally go head-to-head? So here's how the fight plays out. Gravity's pull, remember, is constant. But as our skydiver falls faster and faster, that drag force pushing up gets stronger and stronger and stronger. Then you hit this magic moment where the upward push of drag becomes exactly equal to the downward pull of gravity. The forces are perfectly balanced, the net force hits 0, and acceleration just stops. And that state of perfect balance, that's what we call terminal velocity. It's the top speed, the plateau. The object is still falling, yeah, but it's not getting any faster. It has officially hit the speed limit set by the air itself. And hey, this isn't just theory. For an average skydiver in a headfirst dive, that speed limit is a wild 350 kilometers per hour. But just by changing their shape, spreading out their arms and legs to increase their area and drag, they can slow that all the way down to about 200 kilometers per hour. It's like having air brakes. So we've looked at this whole thing through the lens of forces, but there's another way to see it, a deeper way. It's really all about a great energy exchange. When our skydiver makes that jump, all that stored up potential energy starts transforming into kinetic energy. That's the energy of movement. The more potential energy you start with, the more speed or kinetic energy you can get. It's a pretty straightforward trade. But hang on a minute. If the skydiver hits terminal velocity, their speed stops increasing. That means their kinetic energy stops increasing too. But they're still falling, right? So their potential energy is still going down. So where's all that energy going? It can't just disappear into thin air, can it? Well, here's the twist. Drag is what physicists call a non-conservative force, which is really just a fancy way of saying it's an energy thief. It doesn't let you keep all your mechanical energy. Instead, it siphons it off. All that work done by air resistance converts that falling potential energy not into more speed, but into heat, literally warming up the air molecules the skydiver is plowing through. The energy isn't lost, it's just transformed.
And this constant battle with drag, this isn't just for skydivers. It's a fundamental challenge that shapes the design of pretty much everything that moves fast in our modern world. I mean, just look at a bobsled. That's not just a sled, it's a sculpture in the shape of a bullet. Every single curve is there for one reason, to make its shape and area as small as possible, to crush that drag coefficient, and to slice through the air with the absolute least resistance. And how do they get those shapes so perfect? They use these massive wind tunnels. Engineers spend thousands of hours tweaking every little detail, shaving off millimeters here and there, all in this epic quest to cheat the wind and make our cars, planes, and trains faster and more efficient. And if you're wondering why this matters to you, get this. The next time you're cruising down the highway, more than half of the gas your car is burning is being used for one thing and one thing only, to fight that invisible wall of air. That is how huge of a deal drag is in our everyday lives. From the dimples on a golf ball to the high-tech suits of Olympic swimmers, we've become absolute masters at understanding and manipulating this incredible invisible force. We have literally learned to cheat the wind to go faster and farther. So it really makes you wonder, doesn't it? What's the next invisible force we're going to learn how to conquer?